Welcome to the course on biostatistics and design of experiments. We will look at more designs and how one goes about performing these design strategies. So, we talked about full factorial design, and as you know, full factorial is represented by 2 power n. N is the number of factors, 2 here denotes the number of levels. Of course, you can have 3 power n, 4 power n and so on actually. Initially when you are doing a screening design, that means when you are looking at large number of factors, we generally do it at 2 levels only. Okay. So, the full factorial design may have, if you have 3 parameters, 2 raised to the power 3, that means 2 into 2 into 2, that is 8 experiments and so on actually, 2 power 4, 4 factors, that will be 16 experiments and so on. So, the advantage is that we can look at the interactions, like if you have say 3 factors, 2 raised to the power 3 design, 8 experiments, we can look at interaction AB, AC, BC. In addition, we can also look at the 3-way interaction, that is ABC, but that is also a disadvantage of this full factorial design, because suppose you look at a 2 power 4 design, not only you look at 4 factors, the main effects, you are looking at 6 interactions, that is AB, AC, AD, BC, BD, CD, 6 interactions, but you will look at 3-way interactions like ABC, ACD, BCD and so on, and then you will also look at 4-way. All these are very superfluous, because I did mention that these 3-ways and 4-way interactions are very rare. We generally have 2-way only. So, came into being something called the fractional factorial designs, which are like half of 2 power n, that is 2 n minus 1, or 1/4 of 2 power n, that is 2 n minus 2 and so on. See, these fractional factorial designs reduce the number of experiments dramatically, okay, and we can also get interactions, but there are some disadvantages also in fractional factorial, because unless you choose the number of experiments and where to put in your new factor, you may end up having something called confounding. That means sometimes 2-way interactions may be confounding, and sometimes 1-way interaction may be confounding with the 3-way interactions and so on. So, the fractional factorial design, okay. So, let us look at this. I showed you yesterday also. Imagine I have 3 variables ABC, so 2 raised to the power 3, 8 experiments, everything is okay. Now, I want to introduce another variable D with these 8 experiments. So, it is a half of 2 power 3 or 2 power 4 minus 1, okay. Instead of half of 2 power 3, it is actually 2 power 4 minus 1 design. So, you are doing only 8 experiments. So, I put D here ABC, okay. So, what happens in this, there is an interaction confounding of A with the BCD, B with ACD, C with ABD, confounding, we have to use the correct word. The 2-way interactions are also confounded, AB confounding with the CD, AC confounding with BD, BC confounding with AD and D confounding with ABC, okay. And this confounding, and this is called a resolution 4 design, because we are having D confounded with ABC, okay. And so, the main effects are confounded only with 3-way interactions, and 2-way interactions are confounded, okay. Now, you want to introduce one more variable, 5th variable, that means 2 power 5 design, that is 32, but you want to do only 8 experiments, that means 1/4 of 32, which is 2 power 5 minus 2. So, the question is, if we put E here, what happens? We have main effects confounded with 2-way interactions, okay, main effect confounded with this, which is called a resolution 3 design, because E is equal to CD, right, or E equal to AB, that is called a resolution 3 design, which is generally not liked. Resolution 4 designs are okay, but resolution 3 designs are not okay, because you find a lot of confounding. So, this table gives you a nice idea. So, suppose I have 3 parameters or 3 factors. So, you have a full factorial will be 2 power 3, I want to do half of these. So, 2 power 3 minus 1, that is 4 experiments. So, 4 experiments, we have the AB, instead of AB you put it as C. So, this is a resolution 3 design. Okay. Understand how to understand the resolution, which is not liked very much. Now, let us go to the 4 parameter problem A, B, C, D. I want to do a half fractional factorial design. So, what I do is I take the 2 power 3 model, I mean sorry 2 power 3 design table, and then I will introduce ABC with D. So, such a design is called 2 power 4 minus 1. 2 power 4 is 2 into 2 into 2 into 2, okay, that is 16 experiments. So, the minus 1 gives you half of that, 8 experiments. So, here the design generator is D equal to ABC. So, this is a resolution 4 design because you have 4 variables, no, 1, 2, 3, 4. This is okay. Let us look at another one more variable E. Okay. So, that is 2 power 5, that is 32 experiments. Suppose if I want to do only half of that, 16 experiments, what will I do? E equal to ABCD. This is a resolution 5 design, very nice. But if I want to do 1/4 of 32, that is 8 experiments, 2 power 5 minus 2, then D will become AB or E will become AC. So, this is a resolution 3 design. The main effects are confounded with the two-way interactions, which is not desired, and so on. So, now you know how to do a design generation, okay, and then you can also calculate how to do a resolution calculation. So, many softwares will automatically do this. So, it is a good idea for you to understand it from fundas, so that you can yourself generate the designs, you can even cross check the softwares. Okay. Most important thing is you need to have a balance and orthogonality into the term, and when you are talking about a fractional factorial design, you should have at least resolution 4 design, not resolution 3 design. So, you do not want a main effect confounding with the two-way interactions. Main effect confounding with 3-way is okay, but main effect confounding with the two-way interactions is a resolution 3 design, and generally that is not desired. Okay. So, this is the entire logic of this. These are factorial designs, okay, but then there are many types of designs. There are designs like Taguchi design, there are designs like Placket Merriman design. All these are 2-level designs, and we call it screening design. Okay. Let us look at more of them. Same thing I showed yesterday, resolution 3 design. Main effects are alleged with the main effects are not alleged with main effects, but main effects are alleged with second order interaction. So, that is bad, and second order interactions are alleged with other second order interaction. Resolution 4 design, main effects are not alleged with main effects are alleged with the 3-way interaction, and 2-way interactions are alleged with 2-way interaction. Second order interactions are alleged with second order interaction. Resolution 5 design, no main effect is alleged with any main effect, and no second order interactions are alleged. Okay. Second order interactions are generally alleged with much higher third order. So, resolution 5 is great, but then of course, you need to do more experiments. So, generally resolution 4 is okay. So, as you can see here, we have the A, B, C, D, E type of situation. So, 5 parameters, 2 power 5, that is 32, but we are doing only 8 experiments. So, this is a 2 power 5 minus 2 design, 1/4 of 32 experiments. So, what happened? We put E as ABC, but we put D as BC. So, this is a resolution 3 design, not light, not good. Okay. So, ideally if you want to do a 5 parameter, you must have at least 2 power 5 minus 1 type of experiment, that means 16 experiments. Okay. Same thing here. So, suppose I want to have more variables, say D, E, F, and I want to do only 8 experiments. Okay. This is a resolution 3 design. As you can see, D is equal to AC, E equal to EBC, F is equal to ABC. Okay. So, the I, that is a design generator, is equal to ACD, BCE, ABCF, and so on actually. Again, this is a resolution 3 design. Okay. So, main effects will be confounded with two-way interaction. Okay. So, we will not know whether it is two-way or it is the main effect. Okay. Having done your experiments, imagine you have done say 8 experiments with 3 variables A, B, C, and you got some results. So, this could be say temperature, this could be pH, this could be carbon amount, we have changed it at lower level, higher level. -1 means lower level, +1 means higher level. Imagine I have done 2 raised to the power 3, 8 experiments, a full factorial, 2 level 3 factor. So, 8 experiments and I got some results, say it is a biomass. Okay. Now, how do you identify the main effects? What is the effect of A? What is the effect of B? How do you do that? So, what you do is these 4 experiments are done with the higher level of A, these 4 experiments are done with lower level of A. So, what you do is you add up these 4 outputs, divide by 4, minus add up these 4 outputs, divide by 4. So, that tells you effect of main effect A, understand, because these 4 are plus, these 4 are minus. Okay. So, you add up these 4 to that. Now, if I want to know effect of B, I look at these pluses y7, y8, y4, y3, add up, divide by 4, minus, minuses are y1, y2, y5 and y6, divide by 4. This will tell you effect of B. Effect of C. So, you have 4 places where you have pluses here, 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 here. So, we take y2, y4, y6, y8, divide by 4, minus 4 minuses here, 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 here. So, y1, y3, y5, y7 divided by 4. So, this tells you the main effect. What is the effect of say temperature, what is the effect of pH, what is the effect of carbon. Now, how do we get the interactions? We can do that also. Now, okay. So, look, for example, if T is your A is your temperature, B is your pH, AB gives you temperature into pH, and I told you how to calculate this, right. You know how to calculate this, multiply -1 which is +1. So, minus into minus is plus, plus into minus is minus, minus into plus is plus, and plus into plus is plus. Okay. So, minus minus is plus, minus minus is plus, minus plus is minus, minus plus is minus, plus minus is minus, plus minus is minus, plus plus is plus, plus plus is plus. So, how do you calculate AB? You have 4 places plus, that is y7, y8, y2, y1. So, y1 plus y2 plus y7 plus y8 divided by 4, and you have 4 places you have minus. So, y3, y4, y5 say y6 divided by 4. So, this result will give you the interaction effect AB, very simple. So, when you do a factorial well planned out factorial design, the results analysis also becomes very simple. Okay. First we have the results, then we can perform an ANOVA, we can find out what are the main effects that are important. Okay. Then if there is any interaction also we can calculate using this. So, it is very nice. Now, if I want to know AC interaction, for example, temperature and carbon amount, okay, you know how to get this AC, you just have to multiply these 2 and get this, these 2, this, these 2, this, like that. So, for AC there are 4 places you have plus here, here, here. So, y1 plus y3 plus y6 plus y8 divided by 4, 4 places you have minus, y2, y4, okay, y5 and y7 divided by 4. Same thing with BC, 4 places you have plus, 4 places you have minus. So, you pick up those pluses y1, y4, y5 and y8, add them, divide by 4, minus y2, y3, y6, y7, add them, divide by 4. So, this gives you the interaction effect. So, you can even get ABC effect, because ABC also has the pluses and minuses here. Okay. Suppose if you had made this as a D, that means if you have done a 2 power 4 minus 1 design, that is half of 16, and like I said we can call this as D, although it is a resolution 3 design. Suppose if we have done that D here, then we can get the main effect for D by adding this and this dividing by 4 and subtracting this and divide by 4. Okay. So, you can have got the effect of D also. So, you see the factorial tables are extremely useful. It tells you how to plan the experiments, it tells you how to do the analysis later and do the various calculations. So, that is the main advantage of this type of factorial designs. Okay. So, it is very nice. Okay. There is another design which is also a screening design. It is useful if you have a lot of parameters and you want to screen quickly these parameters, shortlist only a few important ones, and that is called a Placket Merriman design. Placket Merriman design. So, generally it is a multiple of 4, 8, 12, 16. That means you have to do either 4 experiments or 8 experiments, 12 experiments, 16 like that. So, 3 factors can be studied with only 4 experiments. It will give you the main effects. 7 factors can be studied with 8 experiments. It will give you the main effects. 11 factors can be studied with 12 experiments. So, it is extremely good. Quickly we can screen out factors, and ideally if you have say 3, 7, 11, 15, 19, all you have to do is 4 experiments, 8 experiments, 12 experiments, 16 experiments and 20 experiments. Okay. So, it is extremely good for screening variables, large number of variables we can study. So, we will study the main effects at 2 levels, -1 and +1. Okay. There are again you have something called design generator here also in Placket Merriman. Okay, let us look at those design generator. This is the design generator, have a look at it. So, for 8 experiments, design generator is plus minus minus. So, it gives you only 7, please note. So, what do? For variable A we put plus minus minus, and the 8th row is all minus. Do you understand? The last row will always be minus. So, what do? For variable A we put plus minus minus. Now, how do we get these columns? What you do is you take this and put it on top and then push everything down. So, take this, put it on top, and then plus will become plus here, plus will become plus will become plus, minus will become minus, plus will become plus, minus will become minus. And then for C, take this and put it on top and push everything one down. So, this will become here, this will go 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 here. Of course, do not forget that 8th row will always be all minus. Okay. How do you get D? Take this and put it there and then push everything down 1, minus 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 minus, plus 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 minus. E, push it, this plus will come down, this, like that you build it up. Okay. So, you have a design generator for 8 parameters, it gives you 7 numbers here, the last row will be all minuses. So, you put them here in this column and then take the last one, 7th one. This is not the last one, this is ignored generally always. So, you take this and then put it there and then push everything down 1. Take this, put it there, push everything down 1. So, this will come like this. Take this, put it there, push everything down 1. Take this, put it there, push everything down 1. Okay. As you can see here, so you get this. In the 8th row will be all minuses. Again you have to cross check, see it is also a symmetry, okay, balanced. 4 pluses, 4 minuses, 4 pluses, 4 minuses, 4 pluses, 4 minuses, very nice. So, I can screen 7 variables with 8 runs, it is very good, minimum number of variables. Okay, what happened if I had 6 variables? Okay, what do? I can use the same design, I will call one of them as dummy variable. Okay. So, I will use the same. So, you can have one dummy variable. Sometimes if you want 5 parameters and I want to do 8 experiments, 5 parameters and 8 experiments, for example factorial design, it will be 2 power 5, that is 32 experiments, half factorial will be 16 experiments, but I want to do only 8 experiments. So, I take this table and I will put 2 variables here dummy. So, I can do this. So, you see Placket Merriman is extremely powerful in that sense, but you can study only main effects, you cannot study any interaction effects, and ideally because it is in multiples of 4, ideally if your parameters are closer to 4 then it is very good. If not, we can always put dummy variables like that. Okay. Now imagine I have I want to do 12 experiments, that means 11 variables, 3, 4, 5, 6, 7, 8, 9, 10, 11 variables. So, I take this design generator plus plus minus plus 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 minus 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 plus minus. This last row please remember will be all minus. Okay. So, how do I get B? I take this, put it here and push all of them 1. So, this plus will come here, this plus will come here, this minus will come here, plus 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 minus 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 plus. Okay. Do not put anything on this 12th row and so on. So, if I have 11 variables, all I have to do is a 12 experiment, whereas if I want to do a factorial design, 11 variables 2 power 11, which is a huge number. Okay. Even if I can of course look at 1/4 or 1/8 fractional factorial designs also, but this gives you the minimum number of experimental runs, the Placket Merriman design, because for 11 variables I can just do 12 experiments, quickly screen and eliminate many of them which I think is of no use at all. Okay. Then I can go for a detailed design later on. That is the beauty of Placket Merriman design, and these tables I took it from this particular reference. This is a good reference to look at, it is quite simple, and I have been looking at it actually. Okay. So, you have different design generators for the n is equal to 8 experiments or 12 experiments or 16 experiments, 20 experiments, 24 experiments. Remember that last row will be minus always. So, you take the last sign and put it in the next top of the next variable and push everything down and just insert it, that is it. That is how you make that is the design generator for the Placket Merriman design, and this design is extremely useful if you are looking at screening designs, and if it is multiples of 4, nothing like it, use a Placket Merriman design, do not go for factorial or fractional factorial design, because even if you use a fractional factorial design you have some confounding. So, quickly do a Placket Merriman, look at the main effects, remove some of the main effects, take only a limited number and then you do a detailed study. Okay. This is to do with Placket Merriman design. There is something called fold over Kaushal design, 10 runs. You have 4 variables, okay, 4 variables. Placket Merriman design, if I have to do, I can do 4 experiments also. Okay. I can even do half of 2 power 4 factorial design, that is 2 power 4 minus 1, that is 8 experiments also we can do. Okay. This is called a Kaushal design. Okay. These are generated by different statisticians who look at the importance of certain parameters and then they come up with design. So, always remember in any design you will always have a balanced, see look at this, 5 pluses 5 minuses, 5 pluses 5 minuses, that is very important. Any design you are doing it by writing down by hand, always cross check whether balanced is maintained, orthogonality is maintained, that is very important. It is called a Kaushal design. Let us not go too much into this type of design. Placket Merriman is very commonly used in softwares, the factorials are used, then of course the Taguchi designs are also used. Okay. See you have fold over designs for if you are doing 8 experiments, previous one is 10 experiments 4 factors, here you have 8 experiments 4 factors. Okay. So, this is called a fold over design. Okay. This is called a fold over. Why it is called a fold over? You can see I can fold it, it will be exactly like a mirror image, you know, this minus this minus this minus this minus plus this plus this plus. Okay. So, that is why it is called a fold over design. So, ABC you have, and then D variable alone is a new variable you are adding actually. So, if you look at only the ABC portion, it is exactly foldable, you know, this line if you fold it, it is like a the mirror image, right, that is why it is called a fold over design. Then you are adding a new parameter called D. Okay. So, if you have a ABCD fold over design, then we can add a new parameter E in this fashion. Okay. These are called fold over designs. Again, of course, do not forget the balance is maintained, right, that is very important. Then we have the Latin square design. I talked about Latin squares before also. Okay, suppose I have a Latin square design and we are looking at say 3 levels, -1, 0, 1, just like 2 levels we call -1 and +1. If it is 3 levels, generally the methodology they suggest is use 0 as the middle level. So, this is like I am doing 9 experiments, 1, 2, 3, 4, 5, 6, 7, 8, 9, and this is factor B, this is factor C, and this is factor A. Okay. 9 experiments you are doing, okay, 3 into 3, okay, 3 into 3, 9 experiments, look at it, nice symmetry. So, the first experiment will be all the 3 at the lower level, second experiment will be C will be at lower level, A and B at the middle level, the last and third experiment will be C will be at the lowest level, and A and B will be at the highest level, like that, you know. So, you do 9 experiments and the results also we can write down here, and we can do some ANOVAs. We did some problems on Latin square designs, ANOVAs with 3 factors also, if you remember long time back. So, this is called a Latin square design. Okay. So, we have 3 parameters, 3 levels, we are doing only 9 experiments, you can see. Otherwise, if you are doing a factorial design 3 raised to the power 3, that is 27 experiments. If I want to do a 1/3 of that 3 raised to the power 3, okay, that will be 9. Okay. So, it will be 3 raised to the power 3 minus 1 type of experiment. Okay. So, this is called a Latin square because we have a square here and then we put in the factors, the levels of each of the factor, and in the middle also we can put in some factors. If you remember, we did a problem carbon, nitrogen and organism for the production of biopolymer, 7 by 7 Latin squares. Okay. So, again Latin square for ABC, 9 experiments here, right. So, like I said, minus minus minus, that is first experiment, the second experiment will be 0 0 minus 1, third experiment will be plus plus minus 1, like that. This is how you do the experiment, 3 levels. Important to notice, each of the factors there is a balance. 3 times you are doing at -1 level, 3 times you are doing at 0 level, 3 times you are doing at plus level. Okay. Okay. So, it is very well balanced, as you can see here. Okay. Again B also we have 3 times at negative, 3 times at 0, 3 times at plus. Okay. So, this is called the Latin square, and this is we are writing down in the matrix form to do that. So, you do this experiment and you get the results. So, if I want to know the effect of A here, unlike plus and minus we also have 0. So, that means we have effect of A at 3 places, plus, 0, minus. So, we can generate second order type of mathematical relation, whereas if it is 2 levels we will be able to generate only linear type of mathematical relationship. Okay. So, we will continue in the next class. Thank you very much.